Good afternoon, this is Schweitzer. We're going to highlight some some beginning types of calculations that might involve an equilibrium constant and equilibrium concentrations. Since we're getting started with solubility equilibrium, or KSP, remember the SP stands for solubility equilibrium. Now, this really has nothing to do with the main idea. It just gives you a little extra information about the type of chemical reaction that's taking place. In this case, we have a beaker, and inside that beaker, it will have some water, okay? And we're going to dissolve, I got a sample here of some G2SO4, and we're going to drop that in there. Okay, so the first thing I do is I write out the process that's going to be taking place. It's going to be AgSO4. There's two of these. We always start with the solid on the left side, on the reactant side, and then I have produces two Ag pluses and one SO4 minus 2. I leave room below this for my ice table. Keep in mind this is a solid, so solids will not affect equilibrium. In this case, my KSP I usually leave to the right side. KSP will equal the concentration of my products over my reactants. My products are Ag plus squared and SO4 minus 2. My reactants, well, there is only one. It's a solid, so there's nothing. Just leave it as empty or with a 1. Okay, so my general calculations, okay, involve usually wanting to find out my concentrations at equilibrium. So like this box here and this box here, these are two pretty valuable pieces of information. E stands for at equilibrium, or the end. As you dump this stuff in here, and if you were to track it graphically, you'd see that the Ag plus concentration and the SO4 minus 2 concentration both start at 0. At some point, the Ag plus ions and the SO4 minus 2 ions would start to increase in concentration, until one point they just sort of level off. Now the top one here happens to be the Ag plus, and the bottom one is the SO4 minus 2. This guy is twice as big because we get two of these guys every time one of them dissolves. So on the bottom here, I dump it in, I would have the AgSO4, and two of these things dissolve, and one of these guys. Okay, important to get that picture. In this particular solution, because we started with nothing in there to begin with, so there's a 0 bit here, 0 here, the ratio of concentration of Ag plus, okay, is twice that of the SO4 minus 2. Always going to be twice. It's impossible for there not to be two Ags for one SO4 as this stuff dissolves to produce ions. Alright, so again, as it dissolves, had nothing to begin with. They would tell you if there's something there to begin with, and again, only so much can fit in this solution. So that being said, if there was stuff already there, then my current solubility would be lower because there's less room available. Either way, I will gain two of these guys. We call it 2x, and I'll gain x. Now, I don't know how much I'm going to gain, but I know I'll gain two of these for every one of these, and I'm referring to that number as being x. Alright, so this is a pretty standard ice table, and it usually involves something we want to find, which is an equilibrium constant, concentration. So if I want to find the concentration, usually I have to be given the KSP. So let's look up the KSP value. This is a KSP value chart that I usually hand out in class, and you'll find the hopefully silver sulfates on here. Here it is, right here. Okay, 1.5 e to the negative fourth or fifth. Okay, now because when you multiply these two values together, you get the KSP. You should be aware that a higher KSP is going to signify a more soluble substance. So in this case, you could look at this table here and say, okay, well, look at all these values and look how small they are. This is a ratio of products over reactants, where for solubility, the reactant is is nothing. So that means when you multiply the concentrations of those cations and anions together, and any possible squares or that might be involved powers, they're only getting 1.5 e to the negative fifth or 1.4 e to the negative tenth. Real small. And so the least soluble item here could be like the negative 12th. Okay, so very, very negative 18th over here. So very, very, very small insoluble substances. That's where this thing works best. To calculate this thing, in this case, looks like my pen froze here. Give it a second. See if she can get back before I start this video over. Alright, so we'll this video will have to accept that little delay. Alright, so again, smaller numbers equal less solubility, and we showed that on the previous video there, previous slide. So what do I do here? So giving me my KSP, which is going to be equal to 1.0 e to the negative fifth. Let's see if we do this. 1.0 e to the negative fifth. It is going to equal the concentration of each of these guys. All right. Now this guy is representing the silver ion concentration. This guy is representing the sulfate ion concentration. This one is squared. When I want to put these concentrations in, this box represents this box. This box represents this box. And no matter how it works out, those pieces of information right here and here is the same as this. So if I start with nothing, I gain 2x, I now have 2x. Start with nothing, I gain x, I now have x. So 2x represents the concentration of my Ag+, and x represents my concentration of my SO4 minus 2. At this point, we simply solve for x. This process might seem a little complicated, but you do it 2 or 3 times and you realize that it's always the same. This process can go over and over and over again and never change. Different numbers, but it's always the same. 1.0 e to the negative fifth equals 4x squared times x equals 4x cubed. So 2 times 2 is 4, x squared multiplied by the other x is 4x cubed. And then we'd solve out for x. And I would divide by 4, and I'd raise it to the 1/3 power, and that would be equivalent to a cube root. This will give me my x value equaling. Grab a calculator. So we got 1 point. Okay, I got x equaling, in this case, 0.0135, and x stands for our concentration, so it'd be moles per liter. Now this equals the concentration of the what? Go back to our ice table, and we'd see, okay, this is going to be the concentration of the sulfate ion, and if I double it, it would equal the concentration of the silver ion. So at this point, my Ag plus ion concentration or solubility, same thing, SO4 minus 2 concentration, is going to be 0.0135, and the concentration of the silver is going to be 0.0271 moles per liter. They're always assuming it's dissolving silver sulfate. If you're dissolving this compound, silver sulfate, then you have to have a 2-to-1 ratio. Now, if I were to explain a question they might ask, they'd say, what's the solubility of AgSO4? Well, in this case, when I dissolve one of these silver sulfates, so I dissolve one of these guys, I get 2 silvers and 1 sulfate. That proportion will stay true all the time. If I dissolve 10 of these guys, I'll get 10 of these sulfates and 20 of the silvers. So in this case, the solubility of the entire salt will match that of the sulfate. And the solubility of silver sulfate, Ag2SO4, is 0.0135 moles per liter. It's also equal in the concentration of the sulfate ions, and 2 times that will give you the concentration of the silver ion. And I'm going to stop there on this video as being a pretty straightforward method. Quickly, maybe a little review. What we do here is we write out our equation, plug in the information they gave you, write out a KSB expression. At this point, we took the opportunity to solve for an x value. Anytime you're solving for a concentration, you will have an x value like this, and they all work the same. We'll run a couple of examples in future videos.